Hey space travelers! Welcome to the channel where we don't just uncover the secrets of the universe, but the secrets of time itself. Today's topic will blow the mind of not just science fans, but even seasoned physicists. Why do we actually age differently in space? If you love physics, cosmology, philosophy, or sci-fi, don't forget to hit like, subscribe, ring the bell, and share this video with your friends. Because this is a topic people will keep talking about for years. Comment below. If you could control your own aging, would you rather stay on Earth or travel the galaxy knowing that a few years for you could mean a totally different world when you return? Where would you want to pause time? Time, the universe's greatest riddle. Let's start with a simple question. What is time really? For some, it's just a number on a watch. For others, it's an unstoppable river flowing only one way. For physicists, time is simply another dimension, like length or width. And it was Einstein's revolutionary insight over a century ago that proved time is not universal or fixed. Each of us experiences time a little differently, depending on where we are and how we move. Einstein and the birth of relative time. When Albert Einstein introduced his special theory of relativity in 1905 and his general theory of relativity in 1915, he flipped our understanding of reality upside down. Suddenly, time wasn't the same everywhere. What does that mean? Special relativity. The faster you move relative to others, the slower time passes for you. This is called time dilation due to motion. General relativity. The stronger the gravity, the slower time passes. Gravitational time dilation. These ideas create amazing paradoxes and phenomena that have a real impact on our technology, science, and the very nature of aging. The twin paradox. An experiment that changes how we see. Age, perhaps the most famous thought experiment, is the twin paradox. Imagine two identical twins. One stays on Earth their whole life. The other takes a rocket ship near the speed of light to a distant star and returns. When they reunite, the spacefaring twin is younger, even though both experience the same amount of time on their own clocks. The physics behind it? From the point of view of someone on Earth, time aboard the fast-moving ship passes more slowly. For the traveler, less time passes, even though everything feels normal to them. This isn't just theory. This effect is real for all moving clocks, GPS satellites, particles in accelerators, even atomic clocks on airplanes. Gravitational time dilation. When gravity slows down. Your aging general relativity tells us that time passes more slowly where gravity is stronger. On the surface of a planet, time passes more slowly than it does far out in space, away from massive objects. At the Earth's surface, you age ever so slightly less than you would on a mountaintop or in an airplane. At the edge of a black hole, the event horizon, you could live forever. Time nearly stops. Real-life impact, GPS satellites. Their atomic clocks have to be constantly corrected because they are farther from the center of the Earth. Weaker gravity = faster time, but are also moving fast. Slowing time. Without these corrections, GPS would be lost within hours. ISS, astronauts, and milliseconds of youth. You might wonder, what about real astronauts? On the International Space Station, ISS, speed 28,000 kilometers per h and altitude 400 kilometers above Earth combine. Astronauts, thanks to speed, age about 0.01 seconds less over 6 months because their movement slows their time. Meanwhile, weaker gravity at that altitude has the opposite effect. Time speeds up a bit. The effects nearly cancel, but precise measurements show these milliseconds are real. After a year on the ISS, you're just a bit younger than your twin on Earth. In everyday life, it doesn't matter. But in space, where gravity and speeds can be extreme, the differences can be huge. Where are differences huge? Black holes and the speed of light black hole. When time nearly stops, black holes have extreme gravity. If you orbit just outside the event horizon, your time nearly stops. In practice, if you spent an hour orbiting just above a black hole's event horizon, 1,000 years could pass on Earth. Traveling near the speed of light. If you travel at 99.9999% the speed of light, your time slows so much that while 100 years pass on Earth, only a few days pass for you. Combining both effects in theory, you could combine both gravitational and speed time dilation. For example, a ship orbiting a supermassive black hole at high speed would be in a slow time bubble, the perfect way to jump into the future. Impact on interstellar travel and future civilizations. What does this mean for humanity and our plans for interstellar travel? A ship traveling near the speed of light. For the crew, the journey to a distant star might take 10 years, while 1,000 years pass on Earth. When they return, they are visitors from the past, colonies on planets with different gravity. Over very long timescales, differences in population ages can emerge. On Jupiter, time passes slightly slower than on Mars. Civilizations near neutron stars or black holes. For them, time can pass so slowly that they could outlast entire cosmic eras. Pop culture, where have we seen this? Interstellar, 2014. An hour on a planet near a black hole equals 7 years on Earth. This scene is physically accurate, based on Nobel laureate Kip Thorne's real calculations. Planet of the Apes. The hero travels in space, returns to Earth, and finds it's thousands of years older. The effect of time dilation at relativistic speed. Star Trek, Doctor Who. Time travel and time relativity are recurring themes, though often simplified or dramatized. Real-life experiments and measurements, the Haffel-Keating experiment, 1971. 4 atomic clocks were flown around the world on planes, 4 stayed on Earth. Upon return, their times diverged exactly as relativity predicted. Super-accurate atomic clocks. Today, we can measure the difference in time between the ground floor and the top of a skyscraper, several nanoseconds per year. GPS satellites. Their clocks are adjusted daily for relativistic effects. What about our biological aging? You might wonder, will I actually be biologically younger? Yes! From your own biology's point of view, everything is normal. Your cells, metabolism, mental aging all correspond to your experienced time. The difference is in your age relative to others. If you take a mission at nearly light speed, when you return to Earth, your peers may be long gone, while you're still young in your own time. Extreme hypotheses, the elixir of youth, immortality, and time. Travel from a physics perspective, it's possible to stop aging. Just find a strong enough gravity field or move fast enough. But this is beyond our technology and human endurance. A black hole would tear you apart, and no matter we know can survive near light speeds. If we had technology to locally slow time, someone could experience thousands of years in a single day, in a future where everything around has changed. What does it feel like? The subjective experience of time. For an astronaut traveling the cosmos at high speed, everything feels normal. They age just as they would on Earth. It's only on returning that they see the world has aged much faster. It's a bit like flying around the world. Subjectively, nothing seems strange, but objectively, another generation may have caught up to you. What if people could control time? Imagine a civilization that could build gravity generators or travel at near light speed. They could leap into the future, watch the universe evolve, witness the end of stars and galaxies, while only days or weeks pass for them. Time dilation on different solar system bodies. Earth, stronger gravity than Mars, weaker than Jupiter. Our time is in the middle. Mars, weaker gravity equal sign, time moves a bit faster. Jupiter, strong gravity, equal sign time moves a bit slower, though the effect is small. Neutron star, extreme time dilation. You could theoretically watch the end of the universe in a human lifetime, if you survived the conditions. The biggest paradoxes and fascinations. 2 people who grew up together could go on different space journeys and reunite, each a different age, even though subjectively they lived the same number of days. In extreme conditions, you could be forever young, but lose touch with the world you knew. Time isn't a universal constant. It's a variable that defines our aging, our relationships, and our perception of reality. Questions for viewers and engagement. Would you want to travel in time, even if it meant leaving behind everything you know? If you could stop your own aging, what would you do? Do you think humanity will ever embark on true interstellar journeys and become time travelers? How would society change if time differences became common? What's your favorite movie or book about time dilation? Share your ideas, questions, and theories in the comments. The best ones will get a special shout-out in a future episode. Cliffhanger for the next episode. In the next video, we'll explore another cosmic phenomenon. Are there any limits to speed? Or is the speed of light truly the universe's cosmic speed limit? What would happen if we could break it? Thanks for watching all the way to the end. If you love physics, space, time, and all these cosmic mysteries, smash that like, subscribe, and bell, and share this video. Don't miss the next episodes. Because time in our universe never sleeps, and neither should you if you want to understand all its secrets. And remember, time is an illusion, but your comment on this video lasts forever. See you next time in a reality where age can be just a number, if you play by time's own rules.